Morning, everybody. Let's get started. Welcome to the High Energy Density Science Center Seminar Series. I'm pleased to have with us today Dr. Charlie Starrett. Dr. Starrett completed his PhD in positronium collisions with matter at the Queen's University of Belfast in 2007. He changed fields to model warm and hot dense matter as a postdoc at the CEA in Paris, France, and subsequently at Los Alamos National Laboratory, where he is now a staff member in XCP5. His work focuses on the theoretical modeling for predicting equation of state, opacity, and electron and ion transport properties of dense matter. So today's talk is being recorded, so if you're not comfortable with that, please log off. And also please be aware it's an unclassified meeting, and please be aware of any export control issues. If you have any questions and you're logged in virtually, please enter your questions in the chat field and I will read them at the end. If you're in person, please make sure I can pass you the microphone so that people online can hear you well. Otherwise, I hope everybody enjoys, and please take it away, Charlie.
Thanks, Paul. First of all, let me thank you for the opportunity to speak today, and for the organizers for organizing this. It's been really great. Thank you. Okay, so I'm going to talk about some of the progress we've been making in modeling warm and hot dense matter at Los Alamos. This is partly my work, but it's also the work of a huge number of postdocs and students and collaborators. I'm going to focus today on the work of some people. Am I doing this wrong? Okay, it's switched off. So the work today I'll be showing is from all these people, but particularly from Nathaniel Schaefer and Matt Gill, who are highlighted there in red. Okay, so I'm going to frame this like the research was all motivated by these experiments. It was but it was not quite. But we'll go along with that story. So there's been a number of independent experiments that have revealed problems with our approach to opacity at high density. So there was this famous paper by Jim Bailey, the higher than predicted measurement of opacity at solar interior conditions. This came out, I think, in 2015 timeframe. This was followed up by a paper by Tezuki Nagayama and others, where he extended this work not only to iron but to nickel and chromium. And what they found was that the iron measurement in particular was in poor agreement with all the models out there, and all the best models out there could not agree with this. In particular, the bound-free continuum was much higher than the models predicted. And this has important implications for the solar opacity problem, solar abundance problem. I'm not going to get into that. I don't know a lot about it, but I think the basic issue is that they can measure the convection boundary between the convection zone and the radiation zone in the sun using astroseismology, but the models don't predict the same thing. And if the opacity is higher, this would resolve the problem. So when Jim and his co-workers found this higher than predicted opacity, that seemed to indicate there could be a problem with the opacities, could resolve the solar opacity problem. The follow-up study by Tezuki looked at chromium and nickel and didn't find the same sort of problem, but found other problems, and we'll have a brief look at their data in a minute. But then there was these other experiments that looked at continuum lowering by Justin Wark and Sam Vinko's group in Oxford, and they find some differences with the measured data, or with the models again. We're not going to focus so much on those. And of course, we know now, many of us, that there's an effort underway to replicate this iron experiment and other materials at the NIF here at Livermore. So the iron opacity experiment, if true, is a major problem for our modeling, and efforts are underway at NIF to replicate it. Okay, so let's take a quick look at the data. So on the left here we have, these are pictures from Tezuki Nagayama's paper. On the left we have the chromium, iron, and nickel series. And you can see in the middle plot, this is data in black compared to the experiment, compared to the one particular model in red. And you can see that for iron, which is the middle plot on the left, the model is well lower than the experiment. And on the right hand, but for nickel and chromium, which are the top and bottom ones, they're in reasonable agreement with this bound-free region. On the right hand side, we zoom in on this bound regime, and you can see that even for chromium, so first of all, for iron in the middle, there's some agreement in line positions, but there's relatively poor agreement in between the lines. For chromium, there's a similar sort of story, and nickel looks a little better, in my opinion. But none of these models can match these data. So I come from not atomic physics world, but from more of a dense plasma world, density functional theory. So when I saw this, I thought, well, all the models they're using here start from an atomic physics perspective, and then put plasma physics in afterwards as an afterthought. I mean, they might do put a lot of effort into it, but it's still not a consistent model which has the plasma physics baked in. So I thought, well, I can do that. We have models that have plasma physics baked in, so let's see how they do. Okay, so the first one, so how about using our best dense plasma model? And this is density functional theory. Everybody knows what density functional theory is. It's widely used. It's a very powerful technique. A zero temperature, and at finite temperatures, there's an extension due to Merman that makes it valid at high temperatures too. We need, at the time when we started this work, we needed a cone-sham model that could access the high temperatures and can calculate the opacity at high temperature. That was a challenging problem. Only 5, 6, 7 years ago, there was no way to do this. But now there's a couple of ways to do it. But at the time, we thought one way we could do this is with an average atom model. And these are commonly used for equation state model, for equation state predictions across the dense plasma regime, but also the low density everywhere. They're used for the thermal part of the equation of state. So this is a cone-sham density functional theory model. Really what you do in an average atom model is you make your model system where you have a nucleus at the center of a sphere. The sphere size is given by the density of the plasma. And then outside the sphere, you assume a constant potential. And then you use density functional theory to find the electron density of that system. It depends on temperature as an input and density. And then you just solve the Merman-Cohen-Sham problem, and you get this properties of one averaged atom in the plasma. So it's usually used in the US calculations. Here we have a picture of, I think it's the entropy of lutetium over, I don't know, 6 orders of magnitude in density and 5 orders of magnitude in temperature. So you can see it's a model that works everywhere, or at least gives an answer everywhere. And here in this little contour, in this little 3D plot, we just show the idea that the average atom is spherically symmetric. It does have the nucleus, does attract the bound states that are sucked in close to the core. And that's that region of reddish color that shows the high density of the electrons, and then this blue sea of free electrons. So it's a three-dimensional model, but it's spherically symmetric, so it's one-dimensional. Okay, so we can take this and just naively predict the opacity from it. And this is what we get in the picture here. So first of all, this is from our paper. This is from our model, our Tartarus model, which is the average atom model we use at Los Alamos for equation of state. It's sort of like Purgatorio or Inferno. It's very similar in physics content. And this is the prediction of the opacity compared to the Bailey experiment in orange. And you can see these don't look like the same things. They're quite poor, really. So first of all, we get the same. So I've shown this in photon energy rather than wavelength, so it's sort of reversed from the earlier picture. But on the right-hand side, you have this bound-free region, and we're well below the Bailey data, just like all the other models. And on the left here, you have something that looks completely wrong. And these are the bound lines. So why is this so poor? Well, density functional theory averages over the excited states in a system. So instead of calculating the opacity due to all the different excited states, it averages over the excited states and then calculates the opacity of that average atom or average system. So you get one line where you should have, thousands, millions, or even billions. But what we can say is, if we look at the bound free tail, that should be reasonable, because you can make an argument that all those separate contributions should add up to something reasonable, and if the details don't matter, you should be able to do the order averaging in the reverse order and get something reasonable. So it does not explain the BLE experiment clearly, but there are some problems with it. Clearly, it's rather crude plasma physics. It is self-consistent with the electronic structure and the opacity. The plasma physics is self-consistent, but it's rather crude. It's just this ion and a sphere. It also uses this independent particle approximation for the opacity. I haven't really explained that, but basically that just cares about the initial and final state and the matrix elements between them. It doesn't take into account any of the interference effects that can happen in excitations. Yes, sir.
Could you give us a reminder what the plasma? Could you give us please a reminder what the plasma conditions are you're actually modeling? So then the temperature range, maybe coupling parameters. Thank you.
I give them here. So it's 180 eV and 3 × 10⁻²2 electrons per centimeter cubed. So in mass densities, that corresponds to about 1/20 of solid density for iron and 180 eV temperature. Okay. So it's quite hot and quite dense, but not super dense. Okay, so the first thing we did was, well, there was this paper by Kreef et al. In 2018 in the Astrophysical Journal. And what they did was they used a more sophisticated model than an average atom model, where they have a G of R, an ion-ion pair distribution function. It's still spherically symmetric, but it has this ion-ion pair distribution function in it. So it takes into account more physics in a sense than the crude average atom model. And they found some effect on the opacity, but they pointed out in their paper that their model was not self-consistent. And they cited us and said, you guys should do this because your model we had a self-consistent model. So the physics that goes into this model is shown in this equation here. This is called the potential amine force. And what it says is you have a potential created by the ion electrons and the nucleus. That's the VIE. That's the nucleus plus the bound electrons, plus all these surrounding nuclei. Let me see if I can get this to work. Some sort of weird torture. So this is the HII. This is the pair distribution function. And this is the ion electron correlation function. So this takes into account the correlations with the free electrons with the surrounding ions. And this is the electron-electron direct correlation function and the ion-electron pair distribution function. So this takes into account electron-electron correlations and interactions with the surrounding electrons. So there's more physics in it. And this model has been quite successful. Here we have, so this is the sort of physical picture. You've got a nucleus at the origin, you've got a G of R around it, and you solve for the electron density in that system. And we modeled an experiment by Fletcher et al., which measured something called the elastic scattering feature of warm dense aluminum. This was at 6 grams and 2 eV. And they measured this elastic scattering feature. It's sort of like an X-ray Thompson scattering measurement. And they got this data in black, and then we modeled that with this model, this mean force model, and got this red line. And we knew straight away we were on to something because it was great agreement. Not perfect, but great. And we showed in the paper that other cruder models didn't agree with it. This model has some legs to it. It's not completely crazy. But as you can see down here in the bottom plot, if we compare the opacity for this iron experiment between the average atom and the potential mean force in green, they're basically the same. What it turns out, this physics we put in here affects the free electrons, mostly the weakly bound electrons and the free electrons. So it has a tremendous effect for conductivity. And Matt Gill's paper here, which is the one on the top left, showed that we've got reasonable predictions of the conductivity, but the opacity really isn't really affected by this.
There's a quick question from Lauren, whether this is quantum agency.
That's sort of a loaded question. I mean, the short answer is yes. It's not quantum HNC in the sense of Kihara's model, but it's the quantum HNC version that Didier Simon and I came up with around 2013 or so. So improving the plasma physics in this sort of simple-minded way doesn't really improve the problem, doesn't really improve the opacity. It's better for generating conductivities, but does not solve the opacity problem. Okay, so that was the first thing we did. The second thing we did was look at going beyond the independent particle approximation. So this has been solved long ago by time-dependent density functional theory. So Matt, for his thesis, part of his thesis work, developed TDDFT, as it's called, for the average atom model. And this includes some extra physics over the independent particle. So when you have an excitation, there's multiple pathways can happen, and quantum mechanically, you're allowed to have interference between those pathways. TDDFT includes that effect. It also includes something that we normally call in the opacity community orbital relaxation. This is the idea that the orbitals change when the excitation happens. It doesn't include it in the same way we normally think about it, but it does include it to a certain extent. I haven't shown all the equations here, but this is sort of the key one. This is the response function, and the opacity, just take my word for it, is related to an integral over this response function. The independent particle response function is this chi naught. So if you ignore all the rest of those terms, that's what you're doing normally. But if you include these terms, which includes this Coulomb term, let's see if I can get this to this Coulomb term. This is sort of like electron-electron interactions, and the exchange correlation term. This is just the exchange correlation correction to this Coulomb interaction, this Hartree term. So it includes this kernel, and then you solve this problem iteratively. So you start out practically with your initial guess at chi naught, you shove it in here, you do this integral, get a new chi, and then iterate until you can get a converged solution. And the converged solution then can be turned into opacity quite easily. And this is what it does. Again, we're still in the average atom framework, so we still get these horrendous single line features instead of the many lines. But again, the bound could be reasonable. And we focused on the bound here on the right-hand side. So this is the average atom independent particle in black and the TDDFT in red. And then this is the data from Bailey et al. In green with the gray error bars. And it does show a smallish change in the bound free. So that's kind of interesting. It's really hard to get that bound free to move. So that's some effect that was non-zero or non-negligible. But we also observed a similar effect for nickel and chromium of the same order of magnitude. And we need something that's the odd man out for iron to be explained by this. So it's clearly not going to solve the iron problem. Okay. So that was pretty close, but not quite right. And I'll just say before I go on, we haven't solved this problem, so don't get excited. But we tried a lot of things. So maybe the problems with the average atom model, maybe that crude fix we did to the plasma physics by including the GVAR just isn't good enough. You know, it's clearly still a single center approximation, still spherically symmetric, so it's not really that sophisticated an improvement. So we embarked upon a rather long multi-year effort to go beyond that. And this resulted in something called a model based on something called multiple scattering theory. This is originally known, the original incarnation of this was called KKR, Karinga-Kohn-Rostocker. And there's the references down there. You see, this is 1947. This was first came up with. And it even goes back further before the quantum picture. It was done in classical physics. And Kohn here is the same Kohn from DFT fame. They came up with it independently. And this was later developed into other variations, and that's in the umbrella term now it's called multiple scattering theory. So Brian Wilson back, I guess, in early 2014, something like that, around then, published a paper in HEDP that pointed out this method to the plasma physics community and said we could use this. So we took that and ran with it. And the basic idea is you tessellate space. Where are we? Tessellate space into these cells. So this is a 2D cartoon, but the actual simulation is 3D, of course. You have this is a periodic box, and these are the nuclei in orange. And then you tessellate space like a Voronoi tessellation or a power tessellation, and inside each of these cells, which are shown as black lines here, black polyhedra, you solve what's called a single site problem using density functional theory, and you assume some boundary condition. So you can assume a free electron boundary condition, and then the next step is solve Dyson's equation for the Green's function. It turns out you use the Green's function, and the Dyson's equation takes that boundary condition and corrects it so that it's not free electron boundary conditions, but it's matching all incoming and outgoing waves at the cell boundaries. So it gives you the exact solution that you're looking for. And you can see the equation here so the Green's function is just easier to work with. And you end up with this equation here. So it's sum of two terms, a single site term and a multi-site term. I'm not going to go through all this, but you can take a word of it. The density is like an integral over this, over energy for R, and R prime being the same. And this is sort of like a regular solution and an irregular solution. And this is sum over lambda momenta. And what you can show nicely from this is that if you ignore this second term in blue here and make these cells spheres, that is an average atom model. So you can derive an average atom model from this. But if you include this second term and don't make the spherical approximation, this second term, this multi-center correction, corrects all that physics you mentioned in the average atom model. So this is a way forward to a full DFT solution. And multiple scattering theory captures ionic disorder because you use molecular dynamics. And it's all electron, so there's no pseudopotentials, which is a big advantage when you're calculating opacity. And it's practical at high temperatures, which at the time was a big deal because plane wave DFT didn't go up to high temperatures. There are other methods now like SQ DFT developed here. Alex White has one in Los Alamos, this stochastic DFT. And I think there's some other ones as well. But at the time, you couldn't do this. So here's an example of what I mean by ionic disorder, ionic fluctuations. Here's a pressure as a function of time. And here we're moving the atoms with molecular dynamics, and the pressure fluctuates according to this blue line. The average is in red, and this is one standard deviation shown in gray. So this turns out to be a really good model for equation of state. So you can do equation of state with this model, and we have done so I think I'll talk a little bit more of that in a minute, but it can reach high temperatures. You can see here the time. This is for aluminum plasma, 10 eV, 100 eV, solid density, 100th of solid density. Time doesn't really change, 10 to 15 minutes. So it's sort of independent of time, and that's in contrast to plane wave DFT, which goes cubically with the temperature. So this is everything we need, right? It's a plasma physics model. It's full cone-sham DFT. All we need to do is calculate the opacity, and we're done. Well, it's still DFT, unfortunately. So here's the result for the opacity of the Bailey experiment, and you can see Tartarus, which is the average atom model in blue, in red, and the multiple scattering theory in blue. And you can see they're really quite similar qualitatively, and in many cases numerically. For most of it numerically, it certainly doesn't shift up the. Sorry.
It shifts it back.
Sorry.
It shifts the length.
Yeah. So the bind, it broadens them out anyway. But this bind free doesn't change, which is the important thing here, because this is the one bit of the spectrum you can sort of trust. This clearly is not right because it's DFT still. So it leads to very poor spectrum. We're still averaging over the excited states. This is published in this paper here. And we had a student, Crystal Ottaway, who calculated Hugonios with this and published that in Phys Review. Did a great effort calculating the Hugonios. So it turns out it's really good for EOS, and we compared to other good models. We got good agreement. But for opacity, again, this sophisticated plasma physics does not appear to be the solution to the opacity problem. Okay, so we sort of ruled out plasma physics, I think. Almost. So clearly the problem is, the weakness in that argument is that the bound lines are so far off. So how can we really be sure that it's not the DFT that's the problem? Because it doesn't have the many lines instead of the one line. It has one line instead of many lines. So maybe it's some sort of synergy between the many excited states and the plasma physics that causes the problem. So maybe Merman-Cone-Sham DFT isn't good enough. So what we start thinking about is, can we introduce explicit excited states into the model but keep good plasma physics? Now this is not DFT anymore because it's just not DFT. It's something else. So a notable attempt to do this is the superconfiguration approach of Bar-Shalom. I'm not sure Bar-Shalom would have framed it like this, but in this story, that's the way this makes sense. So he came up with this superconfiguration model where you, well, I'm not going to get into this in great detail. So many of you know the superconfiguration model, but essentially the idea is you have these explicit excited states which are described by configurations, and then you collect groups of configurations together in super configurations to make it more numerically tractable, because there can be billions and billions of configurations. And then you can calculate the opacity due to each of these configurations and the transitions between them. And again, Matt Gill, who at the end of his graduate studies transitioned to do a postdoc with Chris Fons and myself. He implemented this superconfiguration model and tried to put in the same sort of plasma physics we have in average atom models. We have this ion sphere model, self-consistent treatment of the bound and free electrons. And he implemented this all in the superconfiguration approach, which is similar to some of the other superconfiguration approaches that exist here, Livermore and elsewhere. And you can see here's the comparison with the iron, chromium, and nickel. The model is in black and the experiment is in green. You can see here is the problem with the bound free again. It does not go away. There are many lines now. It's still not great agreement. The reason for that is this original model of his was non-relativistic and it didn't use the experimental broadening, which would broaden this out more. But it's clearly in the right direction. And he's since done a relativistic model, and it improves the agreement, but it doesn't change this bound free shift. It's still there. So it's much improved over DFT, but the iron problem persists. So that sort of seems to rule out plasma physics plus many configurations approach as the solution to this. There's still one small chink in this argument, which is that superconfigurations as implemented are not variationally derived, which DFT is. And it's not normally used for EOS for that reason, because it's not self-consistent and you don't get a good equation of state out of it. So could this weakness point a way forward?
But didn't you add those explicit excited state configuration when you were doing TD-DFT?
No.
No.
No, you don't. You just start off with the Mermin-Cohn-Sham basis and use that to construct your response function. So it doesn't give you the explicit excited state.
Okay. Well, you just add where the excitation energies are, states themselves.
Well, you get predictions of the excitations energies, and that's what we showed.
Right.
But when I say explicit excited states, I mean that. So if you have a Hamiltonian, it has an excitation spectrum, a list of excited states, whereas whenever you do Cohn-Sham, Mermin-Cohn-Sham DFT, you just have one average excited state due to the temperature. So you don't have populations of all these different excited states. You just have an average population of one averaged excited state. Okay. So there is a variational derivation of superconfigurations, and this was by Thomas Belinsky and Bogdan Shihaki. I think I'm probably pronouncing that wrong, but that's my best effort. However, it appears, and we've talked to Brian and his collaborator Robin Piron, that this is not a practical implementable model. There's no code that exists, and we looked at the formalism and sort of decided it was not practical for technical reasons I won't get into. So we are attempting to derive a simpler model that's similar to Belinsky's model. And what follows for the rest of this talk is going to be some preliminary results from that effort. We haven't got the opacity done yet, but we've got some equation of state stuff. Okay, so this is going to get a little heavy for the next few slides. So don't worry, we'll pick it up again in a few minutes if you don't follow. I'll go slowly though. So basically what you're doing is you're trying to build a configurational model, a model with explicit configurations for this plasma with self-consistent treatment of bound and free electrons. So we start with this average atoms-like extension where you have neutral neutral spheres with bound and free electrons that are connected by a common reference energy, and you construct this constrained free energy. When it's at a minimum, this would be the ground potential, but it's a constrained free energy. Here you have a sum over the configurations in the plasma. This is the probability of the configuration, which is called the population in opacity world. This is the free energy per ion. This is an entropy term. This just says the sum of the probabilities has to be 1. This is a Lagrange multiplier. Here's another Lagrange multiplier, and this term enforces charge neutrality. So when you have your model set up like that, you can just take the derivatives that should be a functional derivative with respect to the density to get the effective potential of each excited state, each configuration. You can then get the probability of each configuration just by enforcing that constraint, and the pressure is just the derivative of the ground potential or the free energy. Okay, so you do that and you get this Boltzmann expression that comes out of the model. So the probability is just e to the minus beta f. Sometimes it's a little confusing because people are used to e to the minus beta u being the internal energy, but f has the entropy in it. And that's usually put out front in terms of like a degeneracy in a opacity world. C here is just the partition function. Pressure comes out to be like this. Many of you won't. Where's it gone? Many of you won't recognize this, but if you're familiar with average atoms, this just looks like the sum over the pressure expression for an average atom model multiplied by the probability of that atom. This is like the probability of one configuration, and that's the pressure due to that one configuration. And then gamma, this Lagrange multiplier, it turns out to be the chemical potential, as you might expect from the ground potential expression. Okay, so that's the model, but I've brushed over one major issue, and that's how you define a configuration in a plasma. So you need this F term. You can write it down formally, but you need to be able to define it, what a configuration is. Now, a configuration in atomic physics is usually thought of as some sort of like, by this sort of terminology here, 1s squared, 2s squared, 2p5, we all learned about in quantum mechanics. That's 2 electrons in your 1s, 2 electrons in your 2s, and 5 in your 2p, for example. And this corresponds to this sort of picture here, where you have these bound levels which you populate. So this has got 6 holes in it, but you only put 5 in it. There might be a 3s with no holes in it, and the 1s and the 2s have got 2 electrons in it. And this is an excited state here, where you've got one of these 2p electrons being shoved up into the 3D. And this is your ground configuration. This is your configuration. So this is a ground configuration, and this is an excited state. So we can define these configurations by listing the ground state configurations. But what if the ground state does not exist? What if the bound state does not exist? So say we need this configuration here, but the 3D doesn't exist. The model tells you it's been pressure ionized, it no longer exists. So what do? You need that configuration for your configuration model, your variational model. You need to know what its energy is to get its probability, but it doesn't exist. So what happens is, so for one density, you've got this configuration, for example, and it may exist, it may have significant probability, but then you incrementally increase the density, it's pressure ionized, the 3D is pressure ionized, and the configuration ceases to exist. So that probability all goes away, it must get shoved in somewhere else. This leads to EOS problems. As you can imagine, the sum of the free energies will change discontinuously when that 3D disappears. Now, this is the approach that's universally used in atomic statistics world. You have these configurations defined by this sort of scheme, and then whenever they become pressure ionized, they just go away. We don't know what happens to them. Okay, so another way to look at this is from a sort of density functional theory perspective, where you have, where's it gone? You have your electron density, which is the sum over all eigenstates. Come on. Of the occupation factor times the orbital squared, which is just the probability density. So if for Fi is the occupation of an eigenstate I, so for F would be equal to 1 for a 1s squared. So the 2 comes from spin degeneracy. So for 1s1, it would be Fi would be a half. So for self-consistent plasma effects, you need not only the list sum over bound states, but you also need the integral over the continuum states. These are the free electrons. So it's sometimes argued that you can use the ensemble average occupation factor, the Fermi-Dirac distribution for the free electrons. However, this breaks consistency between bound and free electrons for the same reasons I talked about in the last slide. And this leads to EOS problems. So is everyone with me? Okay. Because it's a bit tough to know. Okay, so this approach where you treat the bound electrons and the free electrons differently will cause equation state problems. That's my major point. So we need a different approach. So let's just start with something simple. A simple ansatz. So we want to be able to choose a configuration, say this one here that we've been talking about, irrespective of whether the eigenstates are bound or not. So we need to be able to identify this even if a 3D is not bound. So we just extend the definition into the continuum. And this is my definition. I mean, other definitions could exist, but this is my definition. So what you do is you say, well, I want the sum, chi here, chi L is the density of states for a given orbital angular momentum channel. I'm going to define energy boundaries, epsilon L NL, where are you? Epsilon NL, which are the energy boundaries between the bracket, the states, the eigenstates. So in the picture here, what we're doing, this is for the S wave. So E1s would be somewhere below this 1s, and then E2s would be up here. And what your criteria is, the integral of the density states has to be equal to 2 upon 2L plus 1, which is the number of electrons in that state, in a bound state. So you can get from that, you can get a 1s, which is the usual bound type state. Then there's 2s, which in this case is a resonance state. It extends not only over the resonance, but up into the continuum a little. Here. And then the 3s is this configuration now that looks nothing like a bound state, but still exists. And the 4s and so on. And you do this for every orbital angular momentum channel. So the nice thing about this ansatz is it recovers the usual definition for bound states, but it gives a band of energies for the eigenstate in the continuum, which is sort of like what you would expect. But it is just an ansatz. There's not really any formal justification for it other than it's plausible. It allows you to get an energy for these states as they pressure ionize. And will solve the EOS problem because the 3D still exists if it pressure ionizes. So, Brian, is that all right? You believe me? You follow? Okay. Because I know this is a little light there. So here's some preliminary results for this model. We don't have opacity yet, but we've got some equation of state stuff. So here we have the density of states for beryllium 20 eV in solid density. The average atom model is in orange, is Tartarus. And you can see that the multi-configuration model is in blue. And you can see that there's a big spike near the Tartarus spike, and that's due to the configurations that have 1s squared in it. So I've written 1s squared beside it, but all the other spectator electrons, all the other electrons, the other 2 electrons are in other configurations. And that's what leads to the slight broadening you see. The energy is broadened by those other electrons being in other states. So I'm talking about this spike here. And then there's also a bit of spike here at 1s1. This is the configurations that have 1 electron in the 1s. And the other 3 electrons are in any of the other eigenstates. And then we have this continuum type feature. Where is it going? here, you can see there's a bit of a blockiness to it, and that's due to this ansatz. You can see how that density of states would be reflected in the density states overall. So we can consider, for this case, we considered all possible configurations up to a principal quantum number of 6. And that's about 10,000 configurations. So you can see this gets out of hand really quickly. So you solve all 10,000 configurations, the energies of all 10,000 configurations, put them in your model, get the probabilities of those configurations, and get the pressure contribution from each one, and that's what you get. And if we go up to 50 eV, you can see that now the where's it going? The Tartarus line is closer to the 1s1, which means that it's the dominant occupation is 1s1 here, and the 3 electrons again are in other states. There's still quite a population of 1s squared, and here's the similar sort of continuum with this blockiness caused by the ansatz. All right, any questions?
Well, I can get to broaden the 1s1 from Tartarus.
Yeah, that's right. All these are broadened by, I think, 1 eV, because otherwise it would just be delta functions. Okay. So we have some pressure results comparing Tartarus along with ISO core, and there's some difference. This is preliminary, so I wouldn't put too much stock in it, but there is some difference around 40, 50, 60 EV. So I need to dig in. I only got these last week, or earlier this week, so I haven't really thought about them too much, but there is some difference in the equation state. An interesting feature is that you can calculate the charge state distribution. Now, this is a quantity I've struggled with in the past because charge state distribution is sort of like defining what you mean by a bound and free electron. And that's problematic in dense plasmas because you have these partially bound electrons that are hybridized. So are they bound or are they free? I mean, they're clearly free to move between atom sites, but they're not in the free continuum. So here I've picked 2 different definitions. Now, I want to stress that no matter what definition you pick, it doesn't affect the pressure or the opacity in any way. This is just a model. This is just a quantity that we've calculated with the model. It doesn't influence the model. So on the left here, we've defined free electrons as being the nuclear charge minus the number of bound electrons. Okay, so that's what the free electrons are. You may say, well, what else could it be, right? But on the right, we've defined it as the number of free electrons. So the question is, why aren't they the same thing? And the difference is the electrons in the quasi-bound states. The electrons in the quasi-bound states are included in the left-hand picture here, but not on the right-hand picture. So this is why the Z star or Z bar comes out as 2.06 here, whereas it's only 1.79 for this definition. And you can see that these 2 different definitions lead to 2 different charge state distributions. This one has some population of Z equals 2, Z bar equals 2, and some of 3, and this is more continuous. It gives you a more continuous distribution. Yeah. 5 minutes, okay, I'm nearly done. So these, and I put the average atom quantities down here at the bottom. You can see it gives the same Z bar as the average atom, but a different Z star, which is why the pressure is higher. So that's an interesting little thing, I think, about this model. You can get 2 different charges, state distributions, consistent with the same equation state, which is an odd thing to say, I think. Okay, so we're done. Systematic improvements to our physics models have not so far resolved the iron opacity problem or the solar abundance problem. Our model improvements have increased the fidelity of our conductivity and equation of state models. We're working on a configurationally resolved variational model, and we expect this to lead to new insights into equation of state as well as opacity. So thanks for your attention.
Thank you. Thank you very much, Charlie, for the great talk. If you have any questions and you're online, please enter them in the chat field. And there are already several questions. There's a question from S. Eunice who said, could an ensemble DFT approach introduce excited states?
Yeah, I think so. Ensemble DFT is strictly for zero temperature, so you'd have to do something about that. But I think it could do, and Danny Wren at Los Alamos has come up with that proposal, and he's looking into it. So I think it could have something to say about it, but there's some work needs done.
Okay. And there's a question from Carlos Iglesias, who asked the problem with discontinuities in the equation of state configurations, pressure ionizing, may be due to the lack of fluctuations in the model. That is, pressure ionization depends on the local environment, which fluctuates. I guess more of a comment, but
that's more of a comment than a question. I guess he's probably right. I'm not entirely sure what he means by fluctuations.
Okay. And from Stephanie Hansen, it says, thanks for a great talk, Charlie. Does enforcing the 2 times 2L plus 1 to define energy bands lead to significant differences in high N level spacing compared with an isolated ion calculation?
I don't know. That's something I've thought about or looked at.
Did you play around with that constraint and vary that at all?
I have not done yet. There obviously you could choose other constraints, but I've really only come up with this model quite recently, so I haven't played around with it. So the question was whether the principle. Could you read the question one more time?
Does enforcing the 2 times 2L plus 1 to define energy bands lead to significant differences in high N level spacing compared with an isolated ion calculation?
That's a tricky problem because how can you compare them? You know, they're two different things. Like, if it was an isolated atom, it would give the same results. So there would be no difference in the occupation because this is designed to give you the same results for bound states. But if you go to high density, then what does the isolated atom mean? So I'm not sure. I'm not sure.
Fair enough. And then there's a question from Lauren Benedict. When you construct these many all possible configurations, such as in the example on slide 21, are you neglecting any type of orbital relaxation?
So you're not doing the orbital relaxation perfectly, that's for sure, because you have an initial state and a final state, and both of those are relaxed. So they're two different. They're fully relaxed, but you're not doing it properly because when you calculate the opacity from two different Hamiltonians, the eigenstates aren't mutually orthogonal. So there would be that problem, which widely exists, and that's not strictly orbital relaxation, but it's still the same. It's a problem. And you don't have interference between channels like you have in TD-DFT. Of course, you might be able to build that on top of this model, the TD-DFT, but we're not there yet.
And Carlos elaborated on his comment, saying the probability of pressure ionization of any specific configuration without fluctuations is 0 or 1. With fluctuations, it could be between 0 and 1.
Yeah, that's my point, though. You're trying to resolve the fluctuations with this model, right? You're trying to get 0 or 1 occupation. So the Fermi-Dirac is averaged over the fluctuations, but we're trying to resolve the fluctuations, I think, is what he's getting at. Don't think I've really answered that, but
nice talk and good idea here. And I believe you're onto something for the light experiment, and I don't want to make your life increasingly complicated. But if you go to elements like iron, where you have a lot of d electrons, then we know that the s and the p states actually hybridize. So this formula you have up there with the sum over the L sum you might even want to some different L states and bunch them up, because in a solid we know the SP states should be below the D state, but they are buffered in a density of states, and that's because the S state does not fuel its hybridized with the P states. So for heavier elements, it could be even more complicated. Do you have any idea to incorporate this here?
Are you talking about configuration mixing? Yeah, so I mean, this would define a configuration, and then you have to mix the configurations on top of that, like some sort of, CI type model. I'm not sure how you would do that. I mean, you could extend the ideas of configuration interaction that are done with isolated atoms into this regime. But now you've got a band of wave functions, so you'd need to come up with some sort of pseudo wave function that represents the band. So I'm not sure. I think it's a good idea, and it's crossed my mind, but there's a lot of work to done before we get there, I think. But yeah.
Any other questions? No? Okay. Let's thank our speaker again.